All right. Well, hey, happy Friday. Hopefully everybody's doing well. Um, Today, I'm going to show you another method that we can use to help us solve these non-homogeneous differential equations. Last time we saw undetermined coefficients, which lots of algebra, right? But basically, we guessed a form, and then we kind of ran through it and saw, well, what has to be true about these about that form if it's the actual solution. So I'm going to show you another method today that's called reduction of order, and it does exactly what it sounds like it does. It's going to take a second order differential equation and make it a first order differential equation, and those we know how to solve. Okay, so that's my plan. But before we get there, any questions on homework or anything else that you guys would like to talk about?
Just what exactly is a specific solution on what we talked last time, or well, Monday, I guess.
Okay, so when we were doing this, and I think what you're getting at is the form of our solutions, what we should expect for the form of our solutions to these things. Um, Let me just real quickly come back to the whiteboard. Excuse me. All right, so when you have a differential equation, and we're going with second order, so let's just make it nice and generic. So p of t times y prime plus q of t times y equals f of t. All right, so what we know is that the solution is going to be able to be written as yp plus c1y1 plus c2y2. And um, all these y's come from specific places. So y1 and y2, right? These are a fundamental set of solutions to the homogeneous. So if we drop the y and we just look at the f, and we just look at the rest of this, the y1 and y2, they're just going to be fundamental sets to this. So then the other one, the specific solution or the particular solution, that's what this yp is. Okay, so this is called a particular solution. And all it is, this is any function that solves the given differential equation. Okay, so that just means that this piece is such that if you were to do yp double prime plus p of t times yp prime plus q of t times yp, that actually equals f of t. So differential equations have an infinite number of solutions, right? That's what the C's are all about. But what we made use of last time when we were talking about finding a specific or particular solution is we were just finding a function, any function that actually satisfies the differential equation. Because you can then add to that the linear combination of the fundamental set of solutions, and you now have all solutions to your differential equation. So that's what's meant by finding that specific solution or particular solution, is to find a function that satisfies the differential equation, the original differential equation. And last time with undetermined coefficients, we were going with best guess by looking at the form of f. If f had exponential piece, we made a guess of an exponential function as a solution. If it was sine or cosine, well, we looked at made a guess of sines and cosines. If it was a polynomial, we made a guess of a polynomial or any combination thereof. So that's why we did it, and that's exactly what it is. So did that answer your question, Victor?
Yeah.
Okay. All right, so yay, totally works. Make a guess, see what the form is, and basically make it work out. But the problem is we're not always going to have a form that makes sense. We're also not going to always have functions or differential equations where it's really obvious what the fundamental set, right? Sometimes that's hard to do. We have a way of doing it now that if we have constant functions, right? If those are all constant coefficients, we know we make the polynomial, we find the roots depending on the root form, we go. But what if we don't have that? Or what if it's not clear what a way to get our guess and all that? Well, that's where this reduction of order can help out. All right, so I'm going to go hop up to the whiteboard. I will be right back with you. All right. Okay, so what if we had a differential equation like this? So let's just say it was t squared y double prime minus ty prime plus y equals t. Okay, well, knowing what we know, we start thinking, all right, let's start by finding solutions to the homogeneous. All right, so we decided to do that. We change this so that it's homogeneous, and we think about trying to find our y1 and our y2. So we go here, and then you start thinking about it, and immediately you go, nah, we're screwed. Because we don't have a method for doing this because of those t's, right? If those were just numbers, no problem. We are good to go. Okay, so we're kind of sunk even from the beginning. All right, well, I'm curious if you actually can tell me at least a function that satisfies that homogeneous differential equation. Take a look at it and see if you can think of a function that does solve it. Because there's a pretty nice function that does. If you think you have one, go ahead and yell it out or put it in the chat box. I'll give you a hint. It's a polynomial. That wasn't a good enough hint. Well, how about this? I'll just tell you. I know a function that's going to satisfy this is y equals t. Check it out. Its derivative is 1. Its second derivative is 0. So this first part goes away. We have minus t times 1 plus t, which does equal 0. So I think if you actually play around with it a little bit, you would eventually been able to find y1 equals t. And that's actually really good, right? It's good that we found one function that satisfies it because we're halfway to getting our fundamental set. Okay, but what about the second? And that's when you go, well, I have no idea. I have no idea where you begin. All right, well, this is where reduction of order comes into play. All right, so here's the process with reduction of order. in order to do it, you do need to know a solution to the homogeneous. You don't have to have a whole fundamental set, but you need to have at least one solution. So here's what we're going to do. For reduction of order, you do need y1. So if you are given it, or you can find it, the next thing you're going to do is you're going to make a guess, another form of u times y1. So it's exactly the same story that we've done a million times, where we just multiply by u. All right, well, let me show you what happens when we do that. And I'm going to do it generically. We'll come back to this problem and we'll actually answer it here in just a little bit. But let's look at what happens here generically. So I give you a generic one, y double prime plus p of t times y prime plus q of t times y equals f of t. All right, and we already know that y1 is a solution of the homogeneous. All right, well, let's put in the different pieces for y1 prime, or for y prime and y2, or y double prime and so on. So if y is equal to u times y1, then y prime is u prime y1 plus u y1 prime, and y double prime is u double prime y1 plus 2 u prime y prime plus u y1 double prime. You've only written this down in your notes a dozen or so times. It's the same thing every time. Okay, so let's put that into the differential equation. So we're going to get the y double prime plus p of t times y prime. I'm just going to write it p to save ourselves a little bit of writing. And then plus q of y, q times y. Now, what I'm going to do is I'm going to reorder things in terms of the u's. So we're going to get y1 times u double prime. The u primes, we're going to get 2y1 prime plus y1 times u prime. And then the u's, we're going to get y1 double prime plus p times y1 prime plus q times y1. Okay, so if we make the guess of 2 times, this is what we get. But check this out. Look at the piece that's on U. What does that equal? All right, so Ralph just put in the chat box 0 with the question mark. Yeah, I was going to say, let's make it an exclamation, but no, then that becomes 0 factorial, and that's not right. But yeah, no, this is 0. Because remember what y1 is. Y1 is a solution to the homogeneous, which means when we put it into this, we get 0. And that's exactly what happened. Okay, so that part just goes away. So now we're left with y1 times u double prime plus 2y1 prime plus y1 times u prime equals f of t. And hopefully you notice that this actually now can be written as a first order differential equation. If I were to change my letter, let's call it, say, W, so let W equal U prime, then this thing is now linear first order. And linear first order means we know how to solve it. Right? You know how to solve every linear first order. We've got a process for that. And that's what we were able to do here. Okay, so that's why this is called reduction of order, because when you make this guess, what happens is the differential equation now reduces its order. And because it's first order, we can solve it. So that's the process. That's how this is going to play out. But it's super huge. This right here, it's what I wrote at the very beginning. You have to have a solution to the homogeneous. In order to do reduction of order, you already need to know one of the answers. And that's challenging, right? Sometimes it's not always obvious. Okay? But if we can find a solution or given a solution, then yeah, we're good. Okay, so it's not like this is just a miracle and, oh, hey, look, we can always reduce order. No, we definitely have to know something to do it. But if we're in that situation where we do know an answer, we can actually make our life a lot easier. Okay, so let me show you how this plays out. And we'll go ahead. Oh, by the way, don't try to memorize this formula or anything. It's really not worth it. Just every time you're given a function, go through the steps. That's my recommendation. But if you want to try to memorize formulas, yeah, have at it. Okay, so let's actually do this. Let's try a couple of examples where we don't have all of the solutions, but we can actually find part of it. So let's go ahead and start with that one that I put up on the board originally as my justification for it. So we'll look at t squared times y double prime minus t times y prime plus y equals t. And we're going to go ahead and say we know that one of the solutions to the homogeneous is y1 equals t. I told it to you, you see that it works. It's not inconceivable that you would have been able to figure that out if you just kind of fiddled with it a bit, tried different forms. Okay, so now that we know that form, let's use reduction of order. So we're going to go with, let's say that y is equal to u times t. So y prime is going to be u plus u prime t. And then y double prime is going to be 2u prime plus u double prime t. The two u primes, one came from this and the other came from one of the product rule pieces. All right, so let's put those back into our differential equation then and see how this gets changed. So we get t squared times 2u prime plus u double prime t minus t times u plus u prime t plus ut equals t. All right, so we're going to do the same, group them by u's. So u double prime, there's only this piece, so we get t cubed u double prime. the u primes, I've got 2t squared minus t squared, which I believe leaves me just a t squared u prime. And then if we look at the u's, I have minus tu plus tu. That goes away. So hopefully you're all checking my algebra here. But now let's do the reduction of order. So we'll change that u into something else. So again, I'm going to use w. So this becomes t cubed times w prime plus t squared times w equals t. All right, I'm just going to write here that w is equal to u prime to remind us later. All right, well, this guy in green, we can solve. I'm going to start by dividing by the t cubed. So I get w prime plus 1 over t times w equals 1 over t squared. And let's solve this guy. All right, so we go to our techniques for linear first order. So we are going to have to find a W1 and all that kind of stuff. So W1 is going to be e to the negative integral of 1 over t. 1 over t becomes natural log of t, e to the negative natural log of t equals 1 over t. Okay, so then we got to get our integrating factor. I don't want to call it u, but I'm going to call it u. So u is going to equal, or u prime is equal to, remember what our trick is. We come back over here, we have our 1 over t squared. And then we have to divide that by y1. That's 1 over t. So u then is going to equal natural log of t plus c. So w is the product of these. So I'm pretty sure this is when I'm looking at Ralph. Check my math, Ralph. But I'm pretty sure that that's what w actually equals. That's the thing that when we plug it in here is going to give us truth. Okay, so yay, we found w. Well, that doesn't really help because we're trying to find u, but it does help, right? Because we know that the actual u we're looking for, so if we go with the red now, you know that this u prime, it's a different u than that u, is going to equal natural log of t over t plus c over t. All right, so we got to integrate this thing. Well, natural log of t over t, that one if you do a u sub, they call it really u sub because of u prime, but whatever. This is going to give us a natural log of t squared over 2. I'm going to call this guy C1 just because we're going to need another C here. C1 times natural log of t plus C2. All right, so there's u. But now let's go back to the very original idea here. What that u was the thing that we multiplied to t to get our solution. All right, so I'm going to put that back up here. And what we get then is y equals t times all of this. So t times the natural log of t squared over 2 plus c1 t natural log of t plus c2 t. So I'm going to go ahead and circle this, or blob it actually. And just to sort of put a bow on it and everything, so you know what happened. We just found the answer to this differential equation. We found all solutions to that differential equation only knowing one solution to the homogeneous piece.
So that's the general solution.
That's the general solution. I don't, I mean, it's hard because I see your faces, but most people don't actually appreciate the power of this. I mean, think about it. You knew one thing. You knew y equals t, solve the homogeneous. That's it. And yet we were able to get the entirety of it.
And this works for any second order homogeneous differential equation?
It doesn't even have to be homogeneous, right? This one wasn't. This was just equal to t. But so will this process work? Yes, it will work if you know a solution to the homogeneous. Now, before we step off this, I just kind of want to direct your attention to something because there's a lot of power in what I just wrote here. First of all, I want you to notice that I now know a fundamental set of solutions to the homogeneous. I already knew t was 1. Can you tell me what the other function is? You should be able to. Because think about in general when we did this. What's always put on the y1 and y2? The c1 and the c2. So here is a fundamental set of solutions to the homogeneous. T natural log of t and t. We already knew t was. I told it to you. I'm telling you, you would eventually kind of figured it out if you were just playing around. You never would have found t log t, I promise. But try it. Take t log t, take its derivative, second derivative, plug it into this, you're going to get 0. So not only did we find the general solution, we also found the other in the fundamental set. Ooh. The other thing that came out of this is that we found a particular solution. This piece right here, the t squared natural log of t squared, or sorry, t natural log of t squared over 2. That's a yp. That's a particular solution. That is a function that satisfies this differential equation. And when we did undetermined coefficients, we were trying to find them. We got, we made a guess of the form so that we could find yp. This method finds it for you. I love reduction of order. absolutely love it. Yes, there are a lot of steps. I mean, you think about everything that we had to do and how much integration we did on it. Yes, there are lots of steps, but it's insanely powerful. And all it takes is knowing a solution. You know, a solution to the homogeneous, you're good to go. All right, so this is the process. It's given a solution to the homogeneous, make the guess of u times, and then run with it. It turns it into a first order, and we know how to solve first order. So I'm going to show you another example, but before we do that, what can I clear up here? Because I'm certain there are some questions that are lingering. What can I answer and help you see? Okay, I'm going to take that as we're ish, but let's see another example because maybe that'll clear things up or help us see the questions. All right, so here we go. This next one, let's just make it homogeneous. So you can see that the same process works even if it's just homogeneous. It doesn't have to be a non-homogeneous for this to work. So let's go with this. Let's say we've got xy double prime minus 2x plus 1 times y prime plus x plus 1 times y equals 0. So it's clearly second order. It's also linear, right? If you just look at the y pieces, it's linear. It is homogeneous. So all of that's awesome. But again, trying to find a fundamental set of solutions is going to be awfully tough because the only process we know is for one where these things are all constants. All right, so I'm going to help us out. I'm going to help you guys out by telling you that there is a solution to this differential equation that is e to the x. And I bet you guys can see that pretty quickly, right? The derivative of e to the x is e to the x. Its second derivative is e to the x. So if those things are all e to the x's, you just add coefficients. X plus 1 is 2x plus 1 minus 2x plus 1, gone. Okay, so it clearly is a solution. Let's use reduction of order to get get the solution to this entire thing, the general solution. All right, so again, here comes our guess. We're going to make a guess of y equals u times e to the x. So y prime is going to be u prime e to the x plus u e to the x. Y double prime is going to be u double prime e to the x plus 2 u prime e to the x plus u e to the x. So again, I just did the product rule combined. All right, so let's put that back into the differential equation. So we're going to get x times this. So x u double prime e to the x plus 2u prime e to the x plus u e to the x minus 2x plus 1 times the derivative plus x plus 1 times the u e to the x. And now let's group them according to u's. So for the u double prime, we're going to get x e to the x times u double prime. For the u primes, we're going to get 2x e to the x, that's this piece. We're going to get minus 2x e to the x plus e to the x, or sorry, minus e to the x, times my u prime. And then my u's, I already know that it's going to become 0 u's, but I just want to show you. So we're going to get x e to the x minus 2x e to the x minus e to the x from those two pieces. And then this one we're going to get plus x e to the x plus e to the x. But you can see that all of this just goes away. And if I just kind of simplify in here, I get x e to the x u double prime minus e to the x u prime equals 0. Even better, let's divide out e to the x. It's always positive, so we never have to worry about that. So we can cancel that. And we get x u double prime minus u prime equals 0. So this one's really nice, right? Once we do this substitution, man, this thing became really, really simple. All right, so let's do again what we always do. I'm going to call it W. W equal U prime. So this now looks like X W prime minus W equals 0. And we're going to want to solve that for W. But again, we reduced the order. It went from a second order to a first order. And we know all about solving first orders. All right, well, this one, I'm actually going to solve by separating. This becomes dw, or 1 over w times w prime equals 1 over x. So we can do a real quick integral on that one. We get the natural log of w equals the natural log of x plus c. So w is going to, w equals c1 times x. It turned to a multiplication, just like on that one from the exam. It turned into a multiplication because this addition is in the exponent. All right, so there's w. So now we got to get u. Well, we know that u prime is equal to this. So u then is going to be c1 times x squared over 2 plus c2. If you guys don't mind, I'm still just going to call that c1. It's a new c1, but it's c1 times x squared. Which means we're almost done, right? Now we just need to multiply that to our original y, or our original y1. And so we get y is equal to, well, multiply all that by e to the x. So we get c1 x squared e to the x plus c2 e to the x. And notice that this one doesn't have a third piece, right? It just has the c1 and the c2 pieces. And that's because we started with homogeneous. So reduction to order, it actually doesn't care at all. whether it's homogeneous or non-homogeneous to start with, it's still going to bring you to the right place. And similarly, we now know a fundamental set of solutions. We already knew e to the x, because I told you. But even if we had just figured out e to the x works, we now know x squared e to the x also works. Try it. Take its derivative and its second derivative, plug it back into this differential equation, and you'll see that you get truth as well. All right, well, there you go, guys. Let me circle this again. There is every solution to this differential equation. And all we needed to find it was one solution to the homogeneous. All right, so what do you guys think? Like, honestly, what do you think about reduction of order?
It's very cool.
All right, so Victor's on board with me that it's cool. You guys feel like you're going to be able to do it on your own?
It
Like,
looks
what are the
fine.
concerns here? Like, honestly, looking at this,
The
where are you going to
algebra.
run into problems?
Yeah, going to the process and
Yeah, I think the algebraic simplification is what's going to catch me up, honestly.
Yeah, and I mean, man, if that isn't the story of all of our lives in all of the math beyond algebra, right? It's where are you going to get screwed? In here, right? And there are a lot of steps, no doubt. But this is classic monkey math. This is the recipe. Given y1, multiply by u, put in a differential equation. Man, reduce the power, do it again, blah, 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 right? Like, it's very procedural, but lots of steps, lots of algebra equals lots of potential for mistakes and errors. And you make a mistake anywhere, especially early on, blows up. So, because we recognize that, think about how we're going to counter it. Go slow. Pay attention. Watch what you're doing, double check yourself. And at the end of the day, you can always check. Right? Like, I mean, I even hinted at it. Like, literally, I could go, all right, did I do this right? Did I find another one that works? Well, let me try x squared e to the x. So if I've got y equals x squared e to the x, y prime is going to be 2x e to the x plus x squared e to the x. Y double prime, 2e to the x plus 2x e to the x plus another 2x e to the x plus x squared e to the x. All right, so there are all the derivatives. I can fire that back in. Multiply this thing by x gives me 2x e to the x plus 4x squared e to the x plus x cubed e to the x. I'm going to subtract from that 2x plus 1 times this. Well, 2x times that is 2x squared e to the x minus 2x cubed. When I subtract is one of them, minus 2x e to the x minus x squared e to the x. And then add x plus 1 times that. So x cubed e to the x plus x squared e to the x. And then just check it. X cubes. There's 1, 2, and minus 2. Sweet. All those go away. X squareds. Let's see here. Uh-oh. I already know I did something wrong. Shoot. Let's go to the x's. 2x e to the x minus 2x e to the x. Cool, those are gone. I've got a sign error somewhere. X squared x cubed minus one of those. 2x. I've got a sign error somewhere. Okay, so yeah, I just told you, oh, you just got to double check it. And somewhere in my mad dash of doing something, my x squareds don't cancel out. So I got 4 plus 1 minus 1 minus 2. Oh, no, no, that I got it. I got it. This one should be a 4 because it was 2x times 2x. Okay, so anyway, my point is, if you look at the x squared, it's 4 minus 1 plus 1. Those all go away. So I know that x squared e to the x, this is in the null space. That was for you, Victor. So x squared e to the x is in the null space, as is e to the x. They are linearly independent. Therefore, they form a basis. For the rest of you, sorry to get all linear algebra. But
That was my next question, if they form a basis.
Yep. All right. So you can always check. And that is the beauty of this as well, is not only is it nice systematic, you can just plug through and slug through and get your answer. You can always check your answer. And you can use that to help you catch any mistakes along the way. All right, so there you go. There's reduction of order. So we're going to just add that to the list of things that we know how to do. But again, the key is you have to have a solution to the corresponding homogeneous differential equation. If it is homogeneous itself, okay, you know one of the answers. If it's not, you know one of the solutions to the corresponding homogeneous. But once we've got it, cool. We can reduce the order. But that should kind of make sense, right? Like if you think about it, to get solutions to a second order, we need to have two functions. It's kind of like you've got a system of equations and you've got two variables. Well, what happens in a system of equations if you know one of the variables? It reduces it back now to a one equation, one unknown. And that's kind of the same thing here. We're looking for two variables. They're functions, but we're looking for two variables. We found one of them. Well, found one of them. Now we can proceed to find the other. So that's why this works. All right, so I think I'm good for the day. I think we're out of time anyway, or close enough. So just heads up, homework, the next homework sets are due Monday night at midnight. We are still a little bit ahead of schedule. I know. We're over a month in and we're still a little bit ahead of schedule. I don't get it either. But we're slightly ahead of schedule, which means there shouldn't be any homeworks that you don't know the process to work on. I'm not really sure which ones are due on Monday. But anyway, regardless, don't forget homeworks are due on Monday. And beyond that, hey, have an awesome weekend. Enjoy this beautiful weather. And I will see everybody on Monday.